I've always led off discussions of antenna topics with this point. Horizontally polarized antennas at almost any location, no matter how good and no matter how bad, have an advantage over vertically polarized antennas of pretty much guaranteed 6 dB of ground gain. In heavily urban areas with lots of reflections and other things, that's not quite the case. But even in a desert, the ground gain is still about 4 dB, and it's free. For most of us, we obtain the benefit of that ground gain pretty easily on 40 through 10 meters, where the heights that are required are practical for most of us. On 80 and 40 meters, that's hard to do. But it turns out on 80 meters, if you can get a horizontally polarized antenna even at 70 feet or so, you can get this 6 dB of free gain, and it's going to be real hard with a vertical to compete with this unless you put a lot of effort into the ground system for the vertical to keep the ground system losses as low as possible. So for most of us, a dipole or an inverted V dipole at about 70 feet is a really good performer on 80. Unfortunately, in almost all of the world, except if you live real close to the equator, there's no free lunch. For propagation reasons, as well as problems in getting antennas high enough, a vertical is, let's say, except in rare cases, always the best choice, except for some very specialized cases. High-performance antennas for 160, and we're going to quickly go band by band. It's almost always a vertical or a vertically polarized delta loop, but vertical polarization should be well spaced from nearby towers because the other towers interact with it and create directivity that you may not want. And in some cases, that directivity is kind of hard to predict unless you would do a detailed model. So if you can, sometimes you can't, but if you can, that vertically polarized antenna for 160 should be at least 100, 150 feet away from another structure that might interact with it. An inverted L or a T vertical is a really good alternative to a simple vertical, and you can do that with wire supported from trees. As little as 50 feet vertical creates a very effective antenna for transmitting on 160. As little as 50 feet vertical and the rest of it horizontal. And you can learn a lot of details about this just by using Google to search for this stuff. There's a lot of discussion on the top band reflector about these kind of antennas and the pros and cons and how to build them in an optimum way. For all of these antennas, radials on shallow buried, laying them on the ground isn't very practical for survival reasons, but shallow buried radials, 30 to 60 or so, is the best choice. And ideally, at least 130 feet long for 160, but if you can't put them in that long, then that doesn't mean you shouldn't use radials. And if you can't have really radials that are, let's say, more than 65 feet long, a very, very good alternative is a ground screen. You can use chicken wire for that or a variety of other things to create a ground screen, and that's been shown to be quite effective. On 80 meters, for most of us, a dipole or an inverted V about 70 feet high is a real good choice. And for field day, where you're going to work a lot of stations nearby, lower is good for field day and sweepstakes. 50-foot high dipole on 80 will really be an excellent performer for kind of domestic contests. And what I told you about for 160 also applies here. If you put in the effort for a good performing vertical, that is a decent radial system, and get the vertical away from other towers, then these can be good competitors to a high dipole, but you have to really pay attention to the details. Four-square array. They do produce real gain, about 4 dB of gain. There's one other aspect of a four-square that also helps its performance compared to a single vertical, and that is that the ground currents are distributed over a broader area, which reduces the losses. So you have a few dB of reduction in ground losses and 4 dB or so of improved gain from a four-square. And this is a fabulous antenna on 80. And if you don't have an alternative for a horizontal and polarized antenna on 40, a four-square is a good choice. And the good news is we can buy the main thing you need, the controller and the box that goes out at the tower, from a variety of companies. DX Engineering happens to make this one, but there are also some other products. This is the key thing that you need for a Foursquare. Receiving antennas. This is a very detailed topic. So the main thing I'm going to point you to if you're interested in receiving antennas are these websites. So I'm not really going to go into the details here, but if you want to learn more about these, there's lots of information here. Beverage is a fabulous receiving antennas. There's a variety of ways to do it: a single wire, two wire, and there's a company that's just introduced a way of using RG6 cable TV cable as the beverage wire with a box that they sell to make it bidirectional. You can lay a beverage on the ground. One of my fellow PVRC members has a really good website about installing beverages on the ground. If you've got a lot of room, you can use phased beverages. Tom has a really great website that describes that. Something else that's becoming very popular, and the performance of short verticals on 80 and 160 is actually, in many cases, better than beverages. And they're not very big. Typically 20 or 25-foot verticals. High Z antenna sells some fabulous antennas that are very popular. They perform very well. They cover more than one band, and they don't occupy a lot of real estate. So I'd encourage you to visit that website and look at their products. Everyone I know that's used their products has been happy with them. If you have a lot of land, there's an alternative way to build verticals with short antennas, but they require, their directivity is a consequence of the spacing between the antennas. So, and also they need radials in order to provide a stable impedance at the base of each vertical. W8JI has an excellent website that covers these low impedance 25-foot verticals. I have a set of these on 160. The performance is fabulous. My neighbor, W3UR, who used that antenna, was the last station in the United States to work Afghanistan on 160, and he did it right at Afghanistan sunrise, and he couldn't hear a trace of the T6 station on the 1,000-foot beverage, and he made the QSO by listening on a set of these verticals. It's in the log, and he has the QSL to prove it. And that's not just a one-time occurrence. These antennas, both of these, are really fabulous choices. Small loops. If anyone's seen the K9AY loop system, they are amazingly compact. The first time I saw one of those things, I thought, this can't possibly work. It's so small. But for its size and cost, they are remarkable. Little tiny antenna. Anybody can put up one of these K9AY loops, and there's information about those small antennas. For 40 meters, almost everyone who's a serious contester who isn't constrained in a significant way is going to use some kind of a horizontally polarized antenna. Why? 6 dB of free gain. You can't ignore that. Very good performance from a horizontal dipole for DX contest at 70 feet. A 2-element Yagi at 70 feet or a little higher is a significant improvement over a dipole. The Cushcraft XM240 is very cost effective, and it doesn't require a big investment in a tower. Roan 25 is plenty. A ham-4 rotator or a tail twister is a completely adequate rotator for this antenna, and it's a relatively inexpensive and well-proven product. The only thing I'll say about large antennas, they are fabulous, but they will exhaust your bank account. They're expensive antennas. They require large towers and large rotators. So anyone who's considering that, it's a great thing to consider, but don't underestimate the complexity and cost of the effort. It's a challenge, but worth it if you can do it. Beverages and these short verticals are excellent receiving antennas. And in my station, where we have some pretty big transmitting antennas, we often use receiving antennas on 40 meters rather than the transmitting antennas. They work really, really well on 40. We have large antennas, big 3-element Yagis on 40 for transmitting, but for receiving, we often, not always, but we often use beverage antennas for receiving on 40. And short verticals are also a good choice for receiving on 40. And for example, if on 40 you only have a dipole, not a lot of directivity there, and you need some better directivity for receiving, think about a receive antenna for 40. A short beverage, only 100 feet long, will provide good directivity on 40 meters. Or an array of short verticals that occupy only 100 square feet of space, very small space, provides good directivity on 40 meters for receiving. Okay, let me explain this chart, and you're going to see several of these. This chart shows the angle of elevation of the radiation. You see the elevation angle shown here, starting at 0 degrees right at the horizon, and then moving up above the horizon up to about 20 degrees, which is most of the useful elevation angles for DX. And then at the bottom here in decibels, the highest gain antenna, which is a pair of stacked 3-element Yagis, is the 0 dB reference point. So that's not suggesting the gain of this antenna is 0 dB, it's just that that's the reference. And then the single Yagis are about 2 dB down in the case of the real high one, or 3 dB down for useful angles for the one at 100 feet. So this antenna shows that for a really long path like to Asia or VKZL, the real high antenna has an advantage, no surprise there. But if you only have a very high antenna, you're going to suffer real bad up here. You see how that pattern is way down into a null above about 15 degrees radiation angle? If your only antenna is a very high one, you're going to suffer on the money path for DX Contest Europe if you don't have a lower antenna, around 100 feet or even lower. And you'll see this chart for other bands also. So we'll go to 20 meters. Yagis and quads are always the best choice here. If you can't do that, probably a dipole is the next best choice. Verticals on this band are kind of the last choice if you can't possibly do anything else, because you definitely don't get any ground gain from a vertical here. The performance of ground, unless you're at the ocean. Is there anybody here whose shack is at the ocean front? You have an ocean front shack? That's the W1KM, but I'll bet you don't have any 20-meter verticals at W1KM, because even at W1KM in a salt marsh, it doesn't perform as well as a high horizontal antenna. In a salt marsh, 80 and 160 meters are good choices, but even on 40, it's not so good. And that's not your station either, is it? No. Okay, so on 20, you really want to be using a horizontally polarized antenna unless you can buy W1KM's oceanfront location. And for the very best performance, of course, a couple of stacked Yagis. 100-foot tower is kind of the minimum height you want to use for that purpose, but you really would prefer to be a little higher to get the benefit. And if you're going to put 3 stacked Yagis on, you're going to be up in this range to really get a lot of benefit from the high cost of 3 Yagis. So most of us using stacks on 20 are probably using 2 stacked antennas on a tower no less than 100 feet tall. And this is what the performance of a couple of fairly large 20-meter Yagis looks like at 50 feet and 100 feet. Again, the stack is referenced to 0 dB. And you can see, look at the performance of the stack compared to the angles for the kind of the 90th percentile of European signals. It's just about a perfect match. The low antenna is too low for the signals that come in at low angles, and the high antenna is too high for signals that come in at high angles. So when we talk about stacked Yagis for HF, we're not talking about the probably 2 dB of stacking advantage you get. What we're talking about is the diversity of angles that the stack covers. You can see it very, very clearly right here. So at high angles, the stack gives you 6 dB over the high antenna alone. And at low angles, the stack does just as well as that high antenna and gives you about 10 dB advantage of the low antenna by itself. This is what stacks mean on HF, and a lot of people don't get it. But this is what it's about, and the advantage is huge. And you'll notice the competitors are using stacks, and this company has sold thousands of stack matches, and that's why. So the advantage of a stacked array and the ability to do the switching is in the order of 6 to 10 dB rather than 2 or 3 dB. And I'll take questions at the end. 15 meters, again, same story. The heights that you need for really high performance are not as high. You can get really high performance as a competitor up above 70 feet. And if you want to put up stacked antennas, you really need a tower that's 80 to 100 feet tall. And definitely, if you're going to put up stacks, it'd be foolish not to make the small investment in a stack match so you can get full advantage of it. And here's the same story. Look at the advantage of stacks over any antenna by itself. It's an enormous advantage over the European path especially. Many dB, far more than the 2 or 3 dB you might think of as stacking gain. And on 10 meters, the same story again. The heights that are required are much less. A dipole at 25 feet can be a pretty darn good performer on 10 meters when we've got some solar, when we've got some ionization so that the MUF is up above 10 meters. When signals are strong on 10 meters, we all know simple stations work well. And when signals are strong on 10, if all you can do is put up a dipole at 25 feet, you're going to work much of the world. You're not going to compete to Japan with K3LR, but you're going to be able to work stations in Japan and elsewhere. Verticals are probably only in the domain of receiving antennas on 10 meters because the ground gain is just awful. Even at W1KM's oceanfront swamp, salt swamp. Okay, and here's the same chart you've seen before. The stacks have a big advantage over any antenna by itself. Big advantage. And if you make the small investment in a stack match, you can observe that readily, the big advantage of a stack over any single antenna by itself. So let's look at a one-tower antenna system. Most of the people in the room probably have one tower. 50 or 60-foot tower with a small tri-bander or hex beam. Hex beam is a pretty lightweight antenna. You can even put that on a mast. And you can get good performance on all of the bands up through 80 meters with this kind of a small system. You know, you can even build a system like this as a temporary system. There's a portable military tower that was widely available 10 to 20 years ago, the AB577, portable military tower. 3 people can install that portable military tower in less than an hour at a height of 50 feet. And it will easily support small antennas. So you could go to a site away from home and be on the air in a couple of hours with a portable military mast and a small system like this. And you can hang a 160-meter inverted L off the side of that mast. If you want to be more competitive, you can step up to a tower about 70 or 80 feet high and a medium-duty rotator. This is an excellent choice, not very expensive. A 2-element Cushcraft Yagi, a larger tri-bander, the stepper 4-element is one of the many good choices. 80-meter inverted V or a dipole and a 160-meter inverted L. Very effective one-tower station. And if you want to step up to the next level, go up over 100 feet, and a heavier duty rotator. One of the many good choices is the M-square Orion rotator. And a larger tri-bander, this 2-element 40 is still a good choice, and kind of the same antennas but higher. Okay, so now we're going to transition to a different topic, and the area where almost everybody in the room has a problem. Almost everybody. Is there anybody in the room that is absolutely certain that you don't have any problems with any coax cables in your station? One person, and you're wrong. So I'm worried about that guy. And you probably made some mistakes or weather caught up with you. So let's take a look at this, because I'll tell you, I mean, almost everybody in the room has some sort of a problem, and there's a good chance you don't even know about it. And if you don't have a problem now, Next year you probably will. So this is an area that is really important, and most people kind of forget about it. You know, there's nothing sexy about coax cables. You know, you just kind of put them in place and ignore them, and someday you'll find yourself not competing as well as you did on 10 meters. I wonder why. Must be the antenna. Maybe not. Probably the coax. The big problem here is a water and moisture antenna. It's water and moisture entry. It's a persistent threat. Did anybody get woken up by all that hail last night? And the heavy rain? Well, if you go out and look at your tower, take a look at the coax cables during a heavy rain like that. The water is sheeting down those cables. It's pouring down like it's under a waterfall. And any place where there's a defect in the jacket of the cable, and the defect can happen in a lot of ways, or an improperly installed connector, or maybe half the people in this room don't have any waterproofing on their connectors outdoors. All that water that's sheeting down those cables in a heavy wind is going to get into that cable through a variety of ways. And it's not going to make the cable better. It's going to degrade it, in some cases very rapidly. Someone asked me in the previous presentation, how long will coax cable last? If you buy the right cable and install it correctly, 20 years. In most cases, 3 months to 3 or 4 years, because people make serious mistakes and then they get to do it all over again. And they'll probably make the same mistakes again. But 20 years is what you should expect if you only do the right things, and the right things only take a few minutes more. The best choice is some kind of hardline cable. Andrew Heliax, the half-inch diameter LDF4, is commonly available at reduced prices, about $1 a foot in Hamfests, on eBay, sometimes in the classified ads. It's a fabulous cable. Be careful of used cable. If it hasn't been installed properly, you can have some difficulty. But this is a fabulous cable, and you can often buy it for about the same price as new RG213. 75 ohm cable TV cable is also an excellent choice. But in both of these cases, where hams commonly go wrong is in the connection of the connectors to the cable. It's that interface between the cable and the connector that hams usually go wrong, either in the installation, and it takes a fairly high skill level with Heliax to install connectors properly. If you're not sure you know how to do it, find one of your ham friends who knows how to do it, or a professional guy to do it. It won't cost that much money to have a professional guy install those. And if they're properly installed, they have excellent resistance to moisture. The other thing that can happen with RG213 especially, any flexible jacket cable, all of these cables are very susceptible to physical damage. We do field day every year at W3AO, and when I see people unwinding cable and dragging a piece of RG213 over another piece of RG213, what happens is you create a divot in the jacket of the cable as you pull it over another piece of RG213, and that divot turns into a leak. So when you handle RG213, you're handling something that is fragile. And you need to pay attention to what you're doing to be absolutely certain that you don't inadvertently create a leak. And when you create a place where water can intrude, the life of that cable isn't 20 years like it should be with a good quality cable. It might be just the next rainstorm. The other thing that can happen with coaxial cables is that pinholes can develop in the first lightning strike if the cable is not properly installed on the tower, and I'll talk about that a little bit. Pinholes easily happen if the cable is not bonded to the top and the bottom of the tower. And inspection is part of the regime to make sure your investment continues to deliver a return on the investment you've made. So choosing the right kind of cable and connector is really the right thing to do. Surely all of us want to be here, so we want to do all these things. Choose the right cable, install it correctly, and inspect it regularly to make sure that the waterproofing is still there and that nothing has gone wrong. And at the end, we'll discuss a way to actually measure the performance of your cables relatively easy. Coaxial cables are constantly exposed to all of the usual things that happen in the environment: wind, ice, water, condensation inside the connectors, especially in high temperature areas like in the southern part of our country, heat, cold, ultraviolet radiation, especially in places like Arizona and Hawaii, and lightning strikes in most of the country. Lightning strikes are a serious hazard to coaxial cable installations that are not properly installed. And as I already mentioned, the jackets of flexible cable are easily damaged by improper handling and improper installation. If you can avoid using flexible cables going up the tower, that's a good thing to do, because the hardline cables like LDF4 or cable TV cables are highly resistant to damage from lightning strikes, because the jacket has better resistance to poke through. So, but you don't want to use bare 75 ohm cable on the tower. It should be jacketed 75 ohm cable only. But that's a good thing to do. And you don't want to use cables that are susceptible to water. The old style 9913 that has kind of an air dielectric is just an absolutely horrible choice. And I think most people that have 9913 have had terrible problems with it, as evidenced by water pouring out the cable onto the floor in the ham shack. I'll take questions at the end. So the best thing for HF use, for flexible cables, the very best choice is a good quality RG213. There's lots of things that can go wrong with otherwise good cables like LMR 400, but for most of us at HF, we don't need the extra performance of LMR 400. In a good quality RG213 made by a reputable manufacturer, for most of us, is the best choice. Connectors, that's where most of us go wrong. Most of us use N and UHF connectors. There's no difference in performance at HF between these two connectors. They both date from the late 1930s, early 1940s, around World War II. There's only one type of connector you want to use, and I'll show you that. In your stations, there's only one type of connector that you should be using on HF and even 6 meters, and that is a PL259, and a lot of people are surprised by that, but there's no difference there's no significant difference in VSW or loss at 6 meters or HF between a PL259 and an N connector. Why is an N connector a bad choice? It's a very bad choice. The mating force between the center pin of an N connector and the mating female socket, it's a very low mating force. If any minor mistakes are made in the assembly of an N connector onto a cable, that mating force goes down even more. So my strong recommendation is, if anyone is using N connectors in their station on HF and 6 meters, a good plan would be to get that out of your system and replace it with a high-quality PL259 connector. For flexible cables such as RG213, RG213 is the best choice. I'll show you the exact connector to use and no other. For Andrew Heliak's LDF4, there's an aftermarket PL259 of very high quality available from RF Connection in Maryland. I'll show you their website later. If you are using adapters, it's best to avoid them. But if you must use adapters, don't use the cheap Hamfest kind, these nickel-plated things. They are an extremely poor choice. Lots of things are cheaply made in those connectors. So if you have to use one, use the name brand silver-plated adapters. They're often available in Hamfests, but they're silver-plated. And all of the silver-plated adapters I've ever seen are not only high quality on the outside, but the way they're manufactured on the inside is also high quality. So if you have to use an adapter, this is the only way to go. And you are going to be using only UHF connectors, and to use them correctly requires that you tighten them. You don't tighten them just by hand. It doesn't provide a reliable, RF path for the shield of the circuit if you only tighten your UHF connectors by hand. So anywhere in your station you're using UHF connectors, probably a lot of places, if you can put your hand on that connector and loosen it, it's not properly installed. It should be tightened 1/4 of a turn. Biggest mistake going out in the Hamfest tomorrow and spending a couple of bucks on cheap unbranded Hamfest connectors. You know, here you've spent thousands of dollars on your tower and antenna, and you say, oh, I can save $1 by doing this. One of the biggest mistakes you'll make in your entire ham station. This is the only connector that you should be using on RG213, either indoors or outdoors. And it will be marked exactly in this way, Amphenol 83-1SP. It'll be marked on the shell right there. If you see any other digits after 83-1SP, in every case, if there were more digits after that, those are nickel-plated connectors. You don't want to use them. It will be marked exactly in this way. The center pin is silver-plated. The body where the RF flows is silver-plated. This piece is nickel-plated, but it doesn't matter. That's just the mechanical part. And here's where you can get it, Mouser. And there's a lot of other sources too. But if you use other sources, be absolutely sure when you receive the connector that it's marked exactly this way, Amphenol 83-1SP, and no other digits after that. And it's a very high-quality connector, and it costs only $1 or so more than the cheap, I'll answer your question at the end, than the cheap stuff that you'll find outside in the Dayton Hamvention. This is a poor quality photograph, but this is the method that Tim, K3LR, uses to connect a PL259 to RG213. And I think if you look closely here, you can see that the shield of the RG213 is soldered to the outside of the connector. If you go to Tim's website, you'll see the whole process of installing a connector this way. It's easy. The big benefit of this method is you can visually see every aspect of how that connector is electrically and mechanically bonded to the cable. We've all had experiences trying to solder PL259 to RG213, and you're never really quite sure if any of those strands of the braid have broken off inside the connector. Not being sure is not a very good thing. Pretty good chance, if you weren't very, very careful, that you have broken at least one of those fine little pieces of wire off, and it's sitting loose inside the connector waiting for it to fail. Or that you've cut the length of that braid to a slightly incorrect length so that it could short out to the center conductor. So this method that Tim has developed is really the ideal way to do it, and it's not very hard. And I think there are even some YouTube videos that show how to do this to now. Yeah, and it was in QST. It's unconventional, but it is superb. It's the very best way to do it. So you buy the right connector, do it the way Tim does it, and you will have absolutely no problems with that connection, provided you waterproof the outdoor connector and you use a wrench to tighten it. Waterproofing. These are the products that I use. They're not very expensive. They're easily removed when the time comes to take them off. A simple knife will cut through these easily. Follow the manufacturer's directions for the installation of Scotch 130C. Kind of non-intuitive, but the sticky side faces out. And this whole thing amalgamates quickly into an absolutely waterproof barrier. I've never, ever had a connector fail when it's protected by a pretty small investment in this kind of waterproofing approach. What should your feed point look like? The point, probably the most failure-prone location in the coaxial cable system in your station is the place where the coax cable connects to the feed point of your antenna. And every single point here that's shown here is important. So the solder lugs that are used to fasten the cable to the feed point, they shouldn't be the kind of cheap electronic things that you might use in building a piece of electronic equipment. They're going to be heavy duty, noticeably heavy than electronic style solder lugs. And you definitely should have solder lugs here and not a connector. The screws that are used to fasten the feed point to the coax should be stainless steel screws. The nut that's used to hold the whole thing together should be a nylon insert lock nut so that it can't loosen up. Even though we're using a lock nut, we should still use external tooth stainless steel lock washers to guarantee a good electrical bond between the coaxial, between the solder lug and the driven element. Notice very extensive use of tape here to absolutely seal this joint. And not shown here, because it's off the photograph, is the coaxial cable is very firmly fastened to the boom to eliminate vibration and movement in the wind. So this is a simple slide, but every single step here is important, and 90% of you haven't done all of these. You can eliminate almost any possibility of failure of this very failure-prone point in your system by following every one of these points, and it just costs pennies and not very much time. I'm going to jump down to this point. A lot of contesters are into SO2R operation and multi-operation where we like to be able to receive and transmit at the same time, maybe on different bands. The choice of the proper coax cable is a big deal here to avoid the generation of spurious signals in the cables and connectors, and installation practice become even more important, and inspections become even more important when we're trying to transmit and receive at the same time. For a single tower station, if you can buy LDF4, and I don't see any reason why you all can't, this is a fabulous choice. There's no reason to go to any heavier cable than LDF4 unless your tower is more than 200 feet tall. There's no benefit to going to a bigger cable, and it adds more wind load to the tower. If you must use flexible cable, Davis RF Berryflex is acceptable. Notice I don't say it's a great choice. The LDF4 is a much better choice. It's an acceptable alternative for single operator stations only. And the reason it's not a good choice for multi-op stations is when moisture gets into this cable, notice I said when, not if. When moisture gets in, there are dissimilar metals problems inside the Davis RF Berryflex, and it can create intermodulation problems. So my recommendation is in an SO2R or multi-op station, you really shouldn't be using this stuff. You should be using RG213 or LDF4. In a single op station, it doesn't matter. For buried cables or any cable that's laid on the ground, you really can't lay RG213 on the ground, and you definitely can't bury it without some problems. And the same with LMR 400. The service life will be very short if you lay it on the ground or bury it. Coax cable lengths. Again, LDF4 Heliox is a fabulous choice, and it's an excellent cable for lengths up to 300 feet long on 10 meters. And you can commonly buy this in Hamfrest for about the same price as RG213. For SO2R stations and multi-op stations, some of us think it's a good thing in our stations to bundle cables together. It looks neat. But in an SO2R or multi-op environment, it can lead to a significant amount of leakage between the cables because of, well, let me back up just a step. We think about coax cables as being perfect. There's a shield there. The RF is flowing on the inside of the shield. Those cables must be perfect, but they're not. They have resistance. And smaller diameter cables have more resistance than larger diameter cables. Single shielded cables have more resistance than double shielded cables. Double shielded cables have more resistance than hardline. And because the coaxial cables are not perfect by design, they have leakage. And the amount of leakage varies by the diameter of the cable and the quality of the shield. So bundling cables together is an invitation to trouble. So a properly designed SO2R station or multi-op station will not have coax cables that are bundled together. They'll be laying loose, and the coupling between them will be negligible. Don't use nickel-plated connectors. I've already showed you the right connector to use, and you should be using silver-plated adapters if you must use them. Multi-tower stations. Those of us that have multiple towers that are lucky enough to have them often have one of them at a fairly good distance from the station. This is the only situation where the investment in a large cable is worthwhile, but only for quite long distances. There isn't enough benefit to justify the much higher cost, about double the cost typically, of investing in this. You know, you might feel better with a big diameter cable, but you don't get any significant benefit on a 300-foot cable on 10 meters to use LDF5. There's no useful benefit. Be sure these cables are properly installed on your tower so they don't fall off in the next heavy ice storm. So any cable, whether it's Heliax or cable TV cable or RG213, needs to be firmly attached to the tower, typically about once every 5 feet. A very good, inexpensive way to do that is to use number 12 insulated wire. Use it as a tie wrap. You know, we've all used tie wraps on trash bags and other things. A piece of number 12 insulated house wire, solid conductor, not stranded, is a very good tie wrap for fastening cables to towers. And it's reusable, just like a tie wrap. Not indefinitely reusable, but you can remove it and put it back on multiple times. So, and it costs next to nothing. So that's an excellent way to fasten cables. And hard lines, at least once every 5 feet, should be fastened to the tower. And flexible cables, because they are so fragile, should be fastened to the tower at least every 2 or 3 feet to protect them from wind and ice damage. The threat from wind is, and if you look at your tower, you'll see this, if you don't have your cables fastened enough, is they keep slapping against the tower in high wind. Every time it slaps against the tower, the cable is being damaged. Slowly it will fail. You won't get 20 years life out of that cable the way you hope. So for the simple cost of some pieces of number 12 insulated house wire, a few pennies, you can extend the life of your cable by years. Top of the tower. Coaxial cables must be bonded to the top of the tower. Not should be, must be. Why? Lightning damage. When you have a lightning strike, and if you're in a lightning-prone area, and most of the United States, particularly the East Coast, is, and some places like Colorado and Florida are kind of unbelievable. If you have a tower above surrounding objects, and a lot of us want to do that, that tower will be struck by lightning. When it's struck by lightning, if your coaxial cables are not bonded to the top of the tower, the voltage, there's going to be a voltage difference between the coaxial cables running down the tower and the tower itself when thousands of amperes are flowing during that lightning strike. So the way to minimize the voltage difference between the coax and the tower to avoid arcing between the cables and the tower is to bond the cable at the top of the tower, and of course we all know you have to bond it at the bottom of the tower. And I'm sure there aren't 6 people in this room that have their coax cables bonded to the top of the tower. So what happens if you don't do that is when you have a lightning strike, every time you have a lightning strike, pinholes get poked into the coaxial cables running down the tower. And every time a pinhole is put in there, first of all, you won't see the pinholes. But as the water cascades down those cables in heavy rain, like we had this morning, the water will find a path into the cable through those pinholes. And the cable starts to degrade, and you don't get your 20 years of life out of it that you should. And, of course, the cables, I'm sure everyone in this room has bonded their cables to the base of the tower. Ground rods should be galvanized ground rods for the protection of the bottom of the tower. Copper ground rods are no longer considered to be an acceptable choice. The reason is it creates a battery between the potential difference between the copper ground rod and the galvanized tower base and the moist soil between them. And the good news is galvanized ground rods are now readily available, and they're cheaper than copper weld. So for any new installation, you shouldn't be using copper ground rods, and the wire that connects the galvanized ground rod to the tower should be a tinned wire, readily available, tinned copper. So you don't want to be using a copper wire for that connection. If you've chosen to use the right ground rod, you don't want to use the wrong wire. So you want to use tin copper wire. You definitely don't want to use braid. A terrible choice. Direct burial. Oh, yes. Okay. Direct burial, and as I said, this was probably going to not have time for questions, but I'm readily available after the presentation, so you can find me in the super suite afterwards and ask your questions there. Direct burial is a tough thing to do. Conduit really is the thing you should be using, but you can direct bury Andrew Heliax or Davis RF bury flux. Those are direct burial, but in every other case it should be in conduit. A common mistake that people make is they use right-angle plumbing connectors to make turns in the conduit, but what you need to go is to an electrical supplier and use the sweeps that electricians use. They're very gradual bends in the cable. Probably the most susceptible to damage in your station is the coax that allows your antenna to rotate at the top of the tower. And there's lots of places for things to go wrong. Rubbing against the tower. Really, the only cable that's suitable for this environment is RG213. And this cable will suffer from abrasion. It's very unlikely you'll get 20 years of wear out of RG213 in this use. So at least one every 10 years, or whenever you notice any damage, this cable should be replaced at the top of your tower. This is my favorite way to connect 50 ohm coax to a balanced feed, and this is described in September 2012 QST, and there are other good alternatives as well. The coax entry into your home should be through a single point ground system. A very common mistake, and I suspect those of you who have lightning protectors, probably half of you put them in the wrong place where they don't do any good. They do not belong at the tower base. If they are at the tower base, they're not doing any good. They belong at the entry to your station. And if you have them in both places, that's even worse, because the one at the tower base, which is in the wrong place, is going to get more voltage. It's going to break down first, which is going to prevent the lightning protectors in the right place from working at all. RG213 is probably what you use. There are some other good choices if you want to use small cables, commonly available on eBay. Never use end connectors for the reasons I described. All connectors should be wrench tight, and there should be no nickel-plated connectors anywhere in the system. And annual inspections, you can read this after the fact, but every year you should be looking for damage to your system. Everybody's got an SWR meter. Very few of you have a record of the measurements you've made. So when you go home, think about spending a little bit of time measuring the VSWR of every one of your antennas from inside the shack at the center of the band and both edges. And that's it. So you can find me in the contest super suite if you have questions.